So the topic for today's lecture is efficient reductions and the notion of NP-completeness.
Reminder to begin recording if you haven't.
Yes, I started recording. Yeah. Okay, so hopefully you've seen reductions in your first course, and typically the kind of reductions are you're looking at computable reductions, and just to sort of remind you, so let me define a reduction from language L to L prime is a computable mapping F, which is going from 0, 1 star, just mapping strings to strings, such that if x is in L, then f of x is in L prime, and this is an if and only if, right? So if x is not in L, then f of x is not in L prime. So this is the typical definition of a mapping reduction, and it's useful to sort of have this picture in mind. So if this is L, you think of what we like to think of are yes instances and no instances. So think of this, maybe it's better to think of this as the universe of all strings, and that is L, right? The strings that are in the language, so we call them yes instances, and the strings that are not in the language are no instances. Here again is the universe of all strings, and this is L prime. So a mapping reduction maps the yes to yes, and it maps the no to no, right? So yes instances go to yes instances, no instances go to no instances. A reduction is called efficient. It's called efficient, or if f can be computed in polynomial time, or sometimes this would be just referred to as a polytime reduction. Efficient, or sometimes it's called polytime, because there are notions of reductions, of other kinds of reductions which may be even more efficient than, you might think of linear time reductions. And there's been a recent theory of what's called fine-grained complexity, where actually one looks at the specific running time of the reduction, and there's a whole theory built around it. For the sake of this course, efficient will mean polynomial time, unless we say otherwise. And we will denote this. We denote an efficient reduction from L to L prime by L to L prime, and we'll just put a P over there. Sometimes it's common to put a P of n. I'll put either a P or P of n. And this means that L can be reduced to L prime using an efficient reduction. Okay? So this is the notation that we use. This is also, these kinds of reductions, they're called mapping reductions. They're also called Karp reductions, and they're also referred to as many-one reductions. I don't want to get into the theory of this, but there is also a notion of a Turing reduction, where instead of having a computable map, what you say is there exists an algorithm for L that actually invokes an algorithm for L prime. So reduction sort of says if you have an algorithm to solve L prime, that is to decide L prime, I should say decide. If you have an algorithm to decide L prime, a reduction gives you an algorithm to decide L. Right? Because you can just apply the mapping reduction. But moreover, if you think about the, let me sort of draw a picture. I think this will make sense. Okay, so here is a Turing machine. I'm going to call this Turing machine M prime, and I'll say M prime decides L prime. We want M that decides L. So the mapping reduction basically says, okay, so here's your mapping reduction, which we decide F. So you could take X, you convert it to F of X, and you can feed F of X into this machine and just output whatever it outputs. Yes or no. This is a many-one reduction. You could imagine a different machine that uses M prime as a subroutine. So maybe M is actually going to do multiple calls to M prime. It could do multiple calls to M prime and then make an output of yes or no. Right? So this sort of reduction is known as a Turing reduction. In this course, and by and large in complexity theory, computational complexity theory, one looks at mapping reductions, which are actually a more stricter notion of reduction. And these are called Turing reductions, or sometimes they're also referred to as oracle reductions, because it says like you have an oracle. This Turing machine M can use the machine M prime. In this situation, we're only allowed to use the machine once, sort of at the very end. So is this distinction clear? And again, I want to emphasize that we are going to be working with CARP reductions, mapping reductions of this form. And just as a little bit of, sort of history behind this, initially the reductions were defined as Turing reductions by Turing, and then eventually mapping reductions were discovered, and discovered that this gives mapping reductions give a very rich theory. Any questions about that? Okay, good. All right. Just to check, make sure that you all follow what I'm saying. Let me ask you a question. Suppose L has a efficient reduction to L prime. Now, which of these is true? So is it A or B? One is true. Which is true? If L is not in P, L prime is not in P. B, if L prime is not in P, and L is not in P, or is it both? So I'm just going to start the poll and tell me the answers. So which of these is true? Which of these is true? And you can use option D for this is confusing, I don't understand. That will also help me to see if I need to explain anything more. So which of these is true? A, B, or C? Okay, so the answer is A, and let me explain. So let's say L can be efficiently reduced to L prime. Now suppose L prime is in P. So L prime can be decided efficiently. Then let's go back to this picture here. This is polynomial time, and this is also polynomial time. If L prime was in P, then this is in polynomial time. So this entire box here is also in polynomial time. What that implies, what this implies, M prime, if L prime is in P, then M prime runs in polynomial time. F runs in polynomial time because we just said that this is an efficient reduction. Then that would mean that L is in P. Right? So basically, we're saying if L is in P, that implies, if L prime is in P, that implies L is in P. But by taking the contrapositive, what we get is that if L is not in P, that implies L prime is not in P. Okay, so we get the first. We cannot get the second one because, and this is where, the term reduction is a little misleading. Because reduction, you shouldn't think of as reducing the complexity. It's an unfortunate term because I think it gives the wrong impression. What could happen is you can reduce to a very complicated problem. It's like saying that I have a particular problem I want to solve. I can convert that to a more complicated problem. Sure. What this says is, but you cannot convert it, you cannot have an efficient conversion to a more efficient language because, more efficient, so that was badly phrased. But I'm just saying that if you have something that is not in polynomial time, you cannot reduce it to something in polynomial time, because if you can reduce it to something in polynomial time, then that would imply that L is in polynomial time. So any questions about this? This is, please ask me. This is a very, very important concept, and we're going to be this is going to form the bedrock of many things that we do in computational complexity and in this course. If there are any doubts about this, please ask me. Would you like me to explain it again? A, yes, and B, no. Do you want me to explain it again? A is yes, B is no. Okay, so it's 50-50. So let me explain this again. And for those of you who are confused, please ask me questions because that will help me, I can clarify your doubts. So hopefully this picture makes sense. This is what a mapping reduction does. What you think of it as, the mapping reduction converts an instance of L, whether yes or no. So think of any string as an instance. It's an input, and you're trying to decide whether this input is in the language or not. So let's call it an L instance. The mapping reduction converts it to an instance in L prime, meaning that if you have a string and you feed it through the mapping reduction, then the original string is in L if and only if the final string is in L prime. So that gives us this picture here. You start with X, you apply the map. This is the mapping reduction, right? This is this function f that does the map. And you get a string such that X is in the language if and only if f of X is in L prime. Right? So X is in L if and only if f of X is in L prime. And now you have a machine that decides L prime. So you can feed this into M prime and just make that the output. And this entire box here, this is now an algorithm that decides L. This decides L. This decides L prime. So if this box in here is efficient, which means this runs, the M prime runs in polynomial time, And f can be computed in polynomial time because, and this is sort of important, and this is something that I've kind of skipped over. And maybe, let me write this out more precisely. I think I'm skipping a step here. So let me explain this more. So suppose, or not suppose, f of x can be computed in n to the c time for some constant c. And m prime runs in, let's say, n to the d time for constant d. Okay. Now consider the machine M defined earlier. So that is this machine M, this entire machine here. So consider this machine that's been defined. This machine, sorry, I should make this clear. This machine over here, which runs f and then runs m prime. The running time is, so to compute f of x, it's n to the c time. Note that therefore the size of f of x is at most n to the c. Remember, n is the length of x. N is the initial input. Okay, now we're going to feed this input into m prime. M prime runs in n to the d, but the n for m prime is actually going to be the length of f of x. Right? So the input of m prime has length f of x, which is at most n to the c. Therefore, m prime runs in n to the c to the power d time. Right? And this is n to the c plus d. So this is where the closure of polynomials plays a role, which is again polynomial in n. So what that shows is it shows that if L prime is in P, then L is in P. That's what you get. But now take the contrapositive. It says that if L is not in P, then L prime is not in P. And that is what you can assert. Any questions? Any questions?
I just want to verify my understanding. It's almost like you're computing f of x and m prime of the f of x.
Yes.
Sequentially, and they both run in polytime, so it's just an addition polytime.
No, it's not just an addition. You have to be careful because the input to m prime is actually much larger now.
Oh, right, the input might, okay.
So the input has blown up.
Okay.
So it's n to the c plus d plus n to the c, but the n to the c plus d could be your dominant term. Right, so this becomes important. So you have to be careful. Like if you're doing, you cannot, every time you chain a reduction, you start blowing up the input. So you cannot chain a reduction too many times, because then you won't end up in it won't be polynomial time. If it was just additive, then you could do it polynomially many times. So this is a distinction between, yeah, so this is sort of an important point here, right? Because the size increases. And the closure of polynomials is fundamental to this. That when you take a polynomial of a polynomial, you still end up with a polynomial. If you were doing reductions in linear time, then, or let's say quadratic time, then things become a lot more complicated then. Right? So you cannot chain to get, you have to be careful about what you can chain together. Right? If you take a quadratic function of a quadratic function, it's not quadratic anymore. But linear of linear would still be linear. Right? So the thing is, you have to be careful about what kinds of reductions can be chained together. Okay. Now let me ask you a question. It's sort of further testing of the understanding. Okay. Suppose deciding L efficiently is a long-standing open problem. So deciding it efficiently is a long-standing open problem, right? So there's no hope of me solving it in this decade. I am interested. I'm not interesting. Well, I am interesting, but still, I am interested in deciding L prime, or rather interested in finding an algorithm to decide L prime. Okay? And I prove that L can be reduced to L prime. So now here are options. I should give up working on L prime, working on deciding L prime. Okay. I have learned nothing more, so I can continue working on L prime. Okay, you read these carefully, and I can conclude that L, or I should say I have proof that L is hard to solve. So here, deciding is a long-standing open problem. That doesn't mean that there is any proof that it's hard. It's just long-standing open problem. I'm not sure if it's a very hard problem. Many people have tried to work on it, haven't done anything. I'm actually interested in deciding L prime, which is a very different language. Now what I proved was a reduction. I proved that L reduces to L prime. What should I do? Should I give up working on L prime, saying that, this is going to be too hard for me to do? Or is it that this is completely irrelevant? I mean, this is some other language L, which is hard. So I've learned nothing, so I might as well just continue to work on L prime. Or have I actually discovered proof that L is hard to solve? Which, as I said, it's an open problem. No, people haven't been able to do anything, but that doesn't mean there's proof that it's hard to solve. Or by hard to solve, I should say, is proof that L, let me see, cannot be decided efficiently. Okay, so I'm going to now run the poll again. And it's very important. So actually, just to let you know, the tests are going to be of this form. I'm going to ask questions of this form, and it'll be multiple choice. So these are the kinds of questions that I have on the test, not writing proofs. So what should I do?
You're under the assumption that I don't want to work on L, right?
I'm under the assumption I don't want to work on L. Yes, exactly. Like, it's a long-standing open problem. It's unlikely that I don't think that I'm going to be able to solve it efficiently. Like, I'm pretty convinced. So I don't want to work on L. I don't want to work on L.
We don't actually know if L or L prime is in P or not. Do we?
We don't know.
Okay.
At this point, we don't know anything. But it's just that we know that, it seems unlikely that L is in P, that's all. Because many people have tried and they've failed. Of course, that doesn't mean anything, but that's sort of the evidence. Let's just say that I know that people who are way smarter than me have tried to get a polynomial time algorithm for L and they haven't succeeded. Right? So I am pretty convinced that I'm not smarter than I'm not going to be able to do that. Does the question make sense? Like, because if you understand this, I think you will start appreciating NP-completeness when you start like getting what this really means.
That being said, it's possible that L prime is the key to L, but we're also giving the premise here that we assume that L is really difficult.
We assume that L is really the premise is that L is really difficult, and I do not expect to make any progress on finding a polynomial time algorithm for L. And I want you, so while I have this question, I want you to look at the other question that I had. Let me just sort of zoom out a bit. Okay. So I wanted to get these things in together. There you go. We can remove the both. Remember, this is what you know. Now tell me what you should do. Right, we're working under the premise that it is highly unlikely I'm going to design a polynomial time algorithm for deciding L, because it's a long-standing open problem that no one's made progress on. Okay, so does someone want to justify their answer?
Well, I said, or I chose A.
Okay.
Because, if L can be reduced to L prime, then that essentially means that if you solve L prime, then you solve L. And the premise of the question was, we don't think we're going to make any headway solving L. So.
That's right.
Yeah.
So the answer is A. I should give up working on, precisely because of this. I don't expect L to be in P. I don't think L prime, and so this is suggesting that L prime is not going to be in P. I should just give up working on it. Or another way to put this is, remember, I wrote, if L prime is in P, that means L is in P. So if I were to get a polynomial time algorithm for L prime, I would get a polynomial time algorithm for L, and I would make progress on this long-standing open problem, which I don't expect to do. The answer is A. It is very important that you understand this, because this is going to be at the heart of NP-completeness. This is going to be at the heart of NP-completeness. So please ask me questions. Like, if this is not clear, say so. And trust me, like, the first time you see this, you have to do a double take. You have to read this stuff carefully. You have to think, and it can be confusing. So ask me questions, and I can try to clarify your doubts. Is this clear why you should give up working on L prime?
Wait, so do reductions, is it necessarily the case that all the people working on L would have already found this reduction?
No, they would not have discovered this reduction.
So is it like necessarily easier or harder to figure out the L prime when we know this reduction?
So what this reduction does
that
is
they haven't used the reduction to try and find L. Doesn't that change like how difficult solving L is?
No, it does not. This is okay. Good. So thank you for bringing that. This doesn't tell you much about L. If L is hard and you know nothing about L prime, so you start with this problem that's really hard and you reduce it to something else. What you have concluded is what you have reduced to is also hard. Because of this statement here. If L prime is in P, then L is in P. So if L prime was efficient, then L would be efficient. You don't expect L to be efficient, so you don't expect L prime to be efficient. I say expect because in the end, a lot of this, as we talk further, is, there's a conjecture and we believe the conjecture. But let's say that you knew that L was not in P. If you know that L is not in P, then L prime cannot be in P for this reason.
What if you were in a situation where proving that L prime was not in P was also useful to you? So all we know is that this shows that L prime is likely not in P.
That's all. This doesn't tell you if L prime is this other language. This doesn't tell you anything about. It doesn't give you any proof that L is easy or hard, unless you know something about L prime being easy or hard. So this is this is maybe the confusing part, which often, over and over again, this is a common, students will get tripped up on this. When you reduce L to L prime, a hard problem cannot reduce to an easy problem. Otherwise, a hard problem, it wouldn't be hard any longer. An easy problem can reduce to a hard problem. I guess that's why the word reduction is a terrible word, right? Because it actually gives you the opposite meaning. Like the word reduction, it's not reducing the hardness. Like you can reduce any problem presumably to the halting problem. Not necessarily, but but that doesn't tell you anything about this problem. So you can convert your problem into something really complicated. But why does that give you any information about the problem you're trying to solve? On the other hand, if you start with a complicated problem, a hard problem, and you reduce it to the problem you're interested in, then you know the problem you're interested in is unlikely to be solvable or is unlikely to have something efficient, because if you could solve that, then you would have solved the complex problem. Does this logic make sense? It's a little hard for me to gauge because, you're online, I'm online. But ask me a question, make sure that you understand. Okay, so I'm going to poll you again. Do you understand this? Does this make sense? A is yes, B is no. Please explain it again. So A means I understand it, I see why this is true. And B is no, I don't see why it's true.
Wait, so I don't see.
Okay, go on.
Why? So you're saying that L is more than not being P, or L prime more than not being in. So we don't know whether or not it's in P, but we do know that it would be difficult to prove whether or not it's in P.
Yeah, let's just say it's highly unlikely that L is going to be in P.
But does this tell us anything about how difficult it is to prove L prime is in P?
Yes, it does actually. It does tell you about the fact that L prime, because if L prime was in P, then L is in P. If L prime is in P, then L is in P.
Is there any proof for proving that if something's reducible to a problem that's difficult to figure out whether it's in P or NP, that it's also the problem that you're reducing from is also going to be difficult to figure out whether it's in P or NP?
So sorry, I was unable to parse your question. So what you know is this fact here. So okay, does this fact make sense?
Yes.
Right? So what this tells you is that if you reduce L to L prime, then if L prime is easy, L is easy. Because you've actually, by easy, maybe easy,
as in solvable.
Easy or hard are bad words. So let me be more precise. If there is an efficient algorithm for L prime, for deciding L prime, there is an efficient algorithm for deciding L. That's what this says. The contrapositive says, if there is no efficient algorithm for L, there is no efficient algorithm for L prime. That's just the contrapositive. And therefore, if you believe that there is no efficient algorithm for L, this statement will transform your belief that there is no efficient algorithm for L prime. Because if you believe this is true, then you must conclude that this is true.
Okay.
And that's why you should give up working on L prime.
Yeah.
Even though it's just likely, since nobody actually solved L.
What's likely?
Well, it's just, seems like this question depends on how much you want to solve L prime, because I thought you said that L was, it's just a long-standing problem. Do those long-standing open problems ever get decided that they were P all along, or have they always been NP when they finally get solved?
Often when deciding something efficient is a long-standing open problem, and you look at the kinds of methods that have gone into it, you will be careful about, of course, the opposite happens, but we'll see more and more. I mean, this is meant to just give you the ideas behind this. We'll make this more formal. What I could have written here is that suppose there is evidence that L cannot be decided efficiently. Not a proof, but there is some circumstantial evidence that L prime cannot be decided efficiently. Which means the belief is that L is not in P. If you prove this, that belief translates into the belief that L prime is not in P.
Yeah. I didn't want to interrupt your discussion.
Go ahead.
And you just took down the poll about it. My internet had went out like a couple of minutes ago, so I didn't know what the question for the poll was.
Oh, the question was, do you follow or not? So.
Okay.
Yeah. Any more questions on this? Please, this is really important, right? This is like, this is the cornerstone of NP-completeness. Like, understanding this logic is at the heart of understanding why NP-completeness is such a useful concept. It basically boils down to saying, when I have a problem or a language L prime and I am trying to design efficient algorithms for L prime, when should I give up? When do I get evidence that I'm unlikely to find an efficient algorithm for L prime? If I can take another problem where it is unlikely to have a polynomial time algorithm and I reduce it to L prime, then actually I have evidence that it's unlikely that L prime is going to have a polynomial time algorithm. So you don't start with the problem and reduce from L prime, which is the common mistake. You start at a hard language, and we'll make this more formal. So now, with this discussion, let me define what NP-completeness is. L is NP-complete if it satisfies two conditions. L is in NP. Okay, so it's a language in NP. Moreover, for all M in NP, so for all other languages in NP, M can be reduced efficiently to L. Okay? So this is just saying that all the languages, and if only two, then we say L is NP hard. Okay, if it's only two. So NP hard just means the second condition, NP complete means both. So NP complete is a language in NP that is NP hard. So NP complete means, or NP hardness, the second condition means that all other languages in NP can be reduced to L prime. Okay? Now let me ask you a question, and we can discuss this. Suppose, so this is also another way this is described is, these are the hardest problems in NP. Why are they the hardest problems in NP? Because if you have a polynomial time algorithm for any NP-complete problem, you have a polynomial time algorithm for everything in NP. So I'll just sort of state this as a lemma, maybe as a claim or a lemma, that if L is NP-complete and L is in P, then that implies P is equal to NP. Does this lemma make sense? If L is NP-complete and L is in P, then P is equal to NP. And you don't even need the complete here. It's enough to say that if L is NP hard. Why? Because if the second condition holds, like, so look at the second condition. So every language in NP can be reduced to L. Every language can be reduced to L. There is a polynomial time algorithm to decide L. By chaining, by what we discussed earlier, there is a polynomial time algorithm to decide M for every M in NP. So every M in NP is actually in P. But that would imply P is equal to NP because P is a superset of, or NP is a superset of P. So now here's my question. Suppose I prove that some NP-complete problem is not in P. So I was able to prove for some NP-complete problem that there is no efficient algorithm for that problem. So, or NP-complete, maybe I should say language, not problem. Hardest problems are languages. Language is probably more appropriate. Okay, so which of the options are true? So A, all NP-complete problems or NP-complete languages are not in P. I mean, this is badly phrased, but what I mean is no NP-complete language is in P. B, it means that all NP languages are not in P. Or C, there is no implication for any other language in NP. Okay, so here's the question. I prove that some NP-complete problem or NP-complete language is not NP. I prove that there is no efficient algorithm for some specific NP-complete problem. What can I conclude? Can I conclude that all NP-complete languages are not NP, meaning that for any NP-complete language it is not NP? Can I conclude that any NP language is not NP? Or is there really no implication for any other language in NP? So let me launch the poll now. So this is about halfway into the lecture. So I'm going to take we can take a short break here. You can ask me any questions. I'll clarify anything, and then we'll continue. So I'll pause the recording here. Okay, so now that we've defined NP-complete languages, you're probably thinking like, but does there even exist an NP-complete language? I mean, why should there be a language in NP such that you can reduce everything to it? That seems it seems bizarre that such a language can exist. And what I'll show you is a simple construction of a language that's almost like trivially NP-complete. And then we'll discuss the Cook-Levin Theorem, which gives us more interesting languages that are NP-complete. Okay, so consider the following language. Okay, so L is going to be the encoding of a Turing machine, an input X, and 1 to the T. So I'm just doing a unary encoding. So 1, and I just put T1s after it. And I'll say M is a non-deterministic Turing machine that halts in T steps and accepts X. Okay, this is a language which is it's very similar to the universal language. Right? If you didn't have the 1 to the T and you didn't have this, and you just had a normal Turing machine, this is just the universal language. This is like some kind of, think of it as the NP variant of the universal language, where you also give as input how many time steps to run. So this is a valid language. Now L is an NP. L is an NP, right? Because how do you design a machine for this which is non-deterministic? You simply run M on X for so many steps using non-determinism. So L is an NP. And you can actually show, and I'll leave this as an exercise, that for all M in NP, M sort of reduces efficiently to L. Because what does the reduction do? So you know that M is an NP, so there exists some machine, so script M versus, normal M. So normal M is a machine for M, so you create an instance in L by just appending the input and appending the running time bound. Now the running time bound is polynomial. Maybe one thing that I should have clarified here is you need to use an efficient simulation. Right? You use a universal Turing machine to simulate this to show that it's an NP. So is this clear? Why this is the case? Any questions about this?
Could you reiterate why L is an NP?
Why L is an NP? Sure. So so we can think of it in two different ways. So let me give you the certificate view. So for anything in the language, there needs to be a certificate. The certificate has to be of polynomial length. Now the certificate would simply be the non-deterministic choices that this machine has to make. The length of the certificate is only going to be t, because we know it halts in t steps. Right? So the length of the certificate is actually going to be linear in the string. Or, because it essentially tells you the non-deterministic choices to be made. And then you can just do a simulation of the machine on that, use the efficient simulation. So that's why it's an NP. That's a certificate view. And you can also do the non-deterministic Turing machine view as well. Right. Okay, so that's why it's an NP. And then do you see why this should be the case? Essentially, you're literally just going to take the machine, append X, and then pad it with the runtime. This is a padding. This is to tell it how many steps to run. Because you cannot specify, you cannot say run for polynomial time, because then you have to specify the polynomial. And you don't know what the polynomial is. Right? You can't say run in polynomial time. You have to specify exactly how many steps to run. And that's why you pad it. Any questions?
So the reason why it's NP is because, well, it just has to accept a certificate that that will be valid, right? That will allow it to if you include that certificate, it will be decided,
yes.
Right? So as long as we have a certificate that's polynomial in length, right? Then and it accepts or
right.
It decides that, then that would mean that it's an NP, right?
And just to sort of complete the argument, you need to have a certificate that works for things that are in the language, but if it's not in the language, there should be no certificate.
I see. Right.
But you will have that, because if M does not accept X, then no matter what the non-deterministic choices are, it's not going to accept.
I see.
Right? Sure. So you have to get both sides of the argument. Okay. But this is a very contrived language that's NP-complete. And you might think like, okay, so what? So you cooked up some language which is NP-complete. And this is where one of the monumental achievements in computational complexity theory, or actually in computer science as a whole, is the Cook-Levin theorem. Proven by Cook in 71 and Levin in 72. Interestingly, on sort of opposite sides again of the Iron Curtain. So Cook was in the United States, Levin was in the Soviet Union, and they both essentially developed this at the same time, remarkably, like within 1 year of each other. And then people on either side discovered that, oh, this was actually discovered. And the theorem, the Cook-Levin theorem, is that a particular language called SAT is NP-complete. Okay, so let me tell you what SAT is, and then we'll do the proof of the Cook-Levin theorem. So a Boolean formula is an expression with variables, with Boolean variables, x1 to xn, and the symbols not or an AND. So it's just some expression. Okay, so x1 to xn and not x1 to not xn, these are called literals. These are called literals. Right, so an expression, for example, phi, would be something like x1 or not of x2, or sorry, x1 or not of x2 and x3, or not of x5 or x3, x and x7, so on and so forth. Right? It's just some expression of this form. So you can think of it as, instead of using plus minus multiplication, you have these other operators there. Okay? And so phi is satisfiable if there exists a setting of the variables. There exists a setting of the variables that makes phi true. Right? So you can set variables true or false, and when you set these things to be true or false, phi will either be true or false. Now, phi is satisfiable if there is a setting of the variables that makes it true. The language SAT is the encoding of all formulas such that phi is satisfiable. Okay, so any questions about what SAT means? Okay. So SAT is an NP. Okay, so I'll let you pause and think about it and tell me, why is it an NP? So you need to say that for anything that is in the language, there is a certificate that can be efficiently, that there needs to be a certificate that can sort of be efficiently evaluated on phi. Furthermore, if phi is not in the language, no matter what certificate you give, your verifier should not accept. Right? So the verifier should accept a phi in the language with its certificate and should not accept anything that is not in the language regardless of the certificate. So what would the certificate be in this case?
I have an idea.
Okay.
You could just use one possible satisfying assignment and then check that.
Exactly. So a satisfying assignment. So the certificate is a satisfying assignment. And the length of this certificate is polynomial, right? Because you just have to give an n-bit string, and you know that the length of this is going to be at least n, simply because you have at least n variables. Right? Because technically the length is the encoding of this, but you think of it being encoded in sort of the most obvious way. And so the length of the certificate is the number of variables. So is that clear? And note that if phi is not in SAT, then no certificate, or there exists no certificate. Right? Because there is no satisfying assignment, pretty much by definition. Okay? And I should say the encoding, I sort of glossed over this. What is the encoding? You think of it literally as just writing this down in ASCII. Like, that is the encoding. So think of this as basically the ASCII representation of the sentence or the formula. Okay? It's just an ASCII representation. I just encode it in binary. Okay, so this is what SAT is. Okay, is this clear? Okay. Now let's actually go ahead and prove the Cook-Levin theorem. Okay, so the proof of the Cook-Levin theorem. So we just argued that Saturn is an NP. Right, so we just showed that, argued that. So now what we need to show is that for all languages M in NP, M can be efficiently reduced to SAT. So what we need to show is that any language in NP can actually be converted efficiently, or an instance in any language in NP can be converted to an instance of SAT. Okay? So let's consider some M. So consider some language M. Consider, I'll say script M is a language. And there is a non-deterministic Turing machine M. And by this I'll say a standard. So there's a standard non-deterministic Turing machine M that decides M, script M, and runs in at most n to the c steps for all computational paths. Okay, right. So this is what it means for M to be in NP. So the proof goes by something called the Tableau method. So what it says is, so before we, let me first explain what is a configuration. So consider the running of M on an input X. And take any sort of step, any snapshot in time. So here's this machine M. It's running, and look at a particular snapshot. So freeze a snapshot. What are the relevant parameters there? Like what do you need to represent that snapshot? What do you need to represent the snapshot? Any thoughts?
The current position or the current state in the state of the head of the Turing machine.
Okay, so you need to know the state. What else?
You need the tape.
You need the tape contents. You need the tape contents. And you need one more thing.
And the position of the head.
And the position of the head. So if you know these at any point, then you could proceed one more step. This is pretty much like a simulation theorem, right? This is what you need to know to be able to simulate the Turing machine. Now this is constant representation. This is constant. Because it's a polynomial, it's a non-deterministic Turing machine that runs in polynomially many steps. This is at most n to the c. Right? Because that's just how much content there's going to be. The position of the head, you can represent it in binary and do better, but you know that this is also at most n to the c. So it seems that you only need n to the c bits to represent this whole thing. Right? You only need n to the c bits, or O of n to the c bits. Okay, so now let me actually write out, I'm going to represent this as a string as follows. So the configuration is represented by a string of the following form. So I'll just say it's sigma 1, sigma 2, up to sigma k, q, sigma k plus 1, sigma k plus 2, up to sigma l, and l is going to be at most n to the c. So what this means is this is the tape contents. This is the state. And by putting it there, what I mean is the head is pointing there. And head points to the next cell. That's what this means. So this is a string representation of the contents or the configuration of the Turing machine. This is a string representation. So there is a string that represents the configuration of M. So do you see that the string, once you give me the string, I know exactly what the Turing machine, where it is, and I can simulate it to the next step. Is this clear? So now let me construct a tableau. So what is the tableau? I'm just going to imagine filling in all the configurations. Filling in all the configurations. So this is the configuration at t equals 0, t equals 1, so on and so forth. So I know that this has to run at n to the c time. This is n to the c. And this is also, you know, it's technically it's like some O of n to the c, right? Because there's this extra one symbol. So this is like this matrix of symbols. Okay, and now so let me think of this abstractly. Let x t comma k be a so let me just think of it as a variable, not a Boolean variable, a variable in the alphabet union state space, because that's what this is, right? It's the alphabet union state. So it's a variable at the kth position in the tth configuration. So at this point, we're just doing a thought experiment, you know, and we'll see how all of this connects to satisfiability. But the thought experiment is the following. So imagine you just wanted to understand what this Turing machine was doing. So what you could do is you could construct this tableau, this matrix, where xtk, capital XTK, is a variable in sigma union q, because all of these are going to be configuration strings. They're basically strings representing the configuration. Okay? Okay, now I'm going to write something, and then we can discuss, and hopefully it'll make sense. Like, okay. So I'll say x is in the language, because now I have to do the reductions. Let's go back to, I'm sorry, the language was M, right? X is in the language M. If and only if there is a setting of the tableau. By setting of the tableau, it means setting these variables. These variables are not Boolean. They're in this sigma union q. We'll convert into Boolean shortly. There is a setting of the tableau such that the first configuration string, the first configuration is the input. Right, so basically it would have the input written over here, whatever is the input tape. The last configuration is accepting, meaning that the state is accepting state. And the third is that each intermediate configuration follows from the previous configuration using a transition in M, in your machine. Right? So X is going to be in the language if and only if there is some computational path. But the computational path can be represented as a tableau. Right? This is saying if and only if there is a computational path. So all of this is the entire computational path, which we can just think of as a collection of strings. And importantly, there are only polynomially many such things. So is this clear? Any questions about this?
I have a question.
Yes.
So can X be, can it be either a state or a character of the on the tape?
Yes. I said it's
Okay.
in sigma union Q.
Gotcha.
Which you need for this, right? Maybe that's why you asked that question, right? So you need it to be. So right now we're not even talking about Boolean variables, right? So you might say, where is satisfiability? But we'll get to satisfiability first when we understand what does it mean to fill the tableau, right? And so what we'll do is we're going to write each of these in terms of these variables, and then we'll convert those into Boolean variables.
Gotcha.
Okay, any questions? Okay. Now let me ask you a question just so that you can check your understanding. Given a filling of the tableau, right? So basically, suppose I filled up this tableau and I handed it to you. How long to check the conditions 1 to 3? Right, so you know what X is, obviously. Okay, you know what X is. So how long does it take to actually check these conditions? So is it polynomial in the tableau size? And the tableau size, remember, is O of n to the 2c, like O of n to the c times n to the c. Is it actually linear in the tableau size? Or is it exponential? Right? So is it polynomial? Is it actually linear? Of course, linear implies polynomial, but you know what I mean. Give the best possible answer. Okay, so let me just relaunch, the poll. Oh wait, it's not RGB, it's ABC. Sorry, in the other class I've been using RGB. Right, so it's A, B, and C. Right. Is it polynomial in the tableau size? Is it linear in the tableau size? Or is it exponential in the tableau size? And clearly, if you think if it's linear, then you also think it's polynomial. But just how long do you think it needs to? Do you need? Okay, good. So most of you think it's either polynomial or linear. Turns out you can do linear in the tableau size. But if you answered polynomial, that's also fine. Like, I think. And does someone want to sort of explain why? Someone who said it's polynomial or linear? Any comments on that?
Well,
go
I
ahead.
guess I could try.
Sure.
Well, my thought process was, you have the starting tableau, and then there's only a certain...
You mean the starting configuration?
Starting configuration.
Yes.
And there's only, a few different possible other configurations, right? So you just sort of search for the next configuration, and then, after that, there's only, the same thing, right? There's only a few other configurations that you can possibly get to, and you just can continue that until you reach the accepting state, right?
Good. So what you're saying is, if you started a configuration, you know that the next possible configuration has only a constant number of choices depending on the transition function.
Yes.
The transition function, it's some fixed constant, whatever the transition function does, right? The number of choices that it has. So you just check if the next string is one of those valid strings, so on and so forth. Right?
Yes.
And
exactly.
Which is exactly right. And with that, you'll just say, okay, it's some polynomial. If you wanted to be a little careful, you can actually do linear. What you can say is, you know that the head is only going to move by one step. So suppose the head is sitting somewhere here. Well, you know that in the next step, the head is either going to move one step to the left or one step to the right. So what you can do is basically there are sort of these small windows where you just need to check whether the head is moved correctly and written the right symbol. In every other place, the string just doesn't change. The configuration doesn't change. Does that make sense? The head is only going to move one step and everything else is going to remain the same. So it is possible to do all of these, and it's possible to check all of these in polynomial time. And we can, okay, so let's sort of,
well, actually,
yes,
in terms of checking whether the head is well, the head needs to be in one of those, or like it can only move, or it can only stay where it is, move to the right or move to the left. But wouldn't you still have to check the rest of it as well? Because, for example, there could be another instance of the head somewhere.
Right, so you do need
illegally placed.
Right, so you need to just check that in all other places the head is not present and the configuration is the same from one step to the next. You do have to make that check. I'm just saying, but the entire thing will be linear in the tableau size.
I see.
Because you can just look at these sort of like, 3x2 windows throughout, and you just check every possible window and make sure things are correct. So let's break this Tableau checking down into a few more specific sort of steps, and then from there we can convert. Now this is where the Boolean formula is going to come in. If I can encode all of this as a Boolean formula, then I have done my reduction to satisfiability. And that's really what the Cook-Levin theorem says. So what I can break down is into these following conditions, which I'll write down. I'll say unique, and I'll encode this as a Boolean formula. xtk takes only one value in sigma union q. This is sort of obvious. Start, we'll say that x0k is the kth input symbol, or maybe I should say k plus 1, because x00 and x00 is the initial state. And you can consider the tape is going to be semi-infinite, like it's only infinite in one direction, just to make things easier. End, we'll say that, you know, one of x, in this case it's like n to the c. Okay, so one of the symbols is an accepting state. And then we have a fourth condition that will say move, which just says that, you know, xt star, which means this is the tth configuration, follows from x t minus 1 star, which is the t minus 1th configuration. So we will break it down. We will break down these conditions into these conditions, and then we will convert each of these into a Boolean formula. We'll convert each of these into a Boolean formula by introducing certain Boolean variables. And, you know, once we do that, then it just becomes sort of a mechanical, it's a mechanical process to start converting each of these into a Boolean formula. And, you know, I'll do a few, and then, you know, I'll do this in the next lecture because we're basically out of time. And after that, you'll see that it's relatively straightforward. And this would then give the full proof of the Cook-Levin theorem. So I'll stop here, and I'll take any questions that you have.